Hello everyone, welcome back. So in this video we'll try using the pumping lemma to take an example of a language and then use the pumping lemma to prove that that language is not regular. So we'll take our very popular example, which is a to the power n b to the power n, where n is greater than 0. So this is my L, and I have the steps written right here. So the first step is to assume that L is regular. Alright, so I've assumed that L is regular now. What that means is that it has a pumping length, so I take a pumping length P. So let's just say that in my case the pumping length is K now. And the next step is to take a string S longer than P. The simplest way I can think of is I just take the string a to the power k, b to the power k. So this is obviously longer than k because the length of this string is 2k. Next, what I have to do is I have to divide S into x, y and z, and I have to take all possible ways. So we've already seen before that there are three ways that I can do this. So let's take our different cases. So I have case 1 here. Case 1 is that y is in the a part, So what that means is that the a part is now split into x, y and z as well. Z could also be in the a part because consider this. Let's say I have a, b, b, b. I could say that this is x, this is y and this is z. So that's still valid. So all I'm saying is that y is in the a part. So I'll have to take a generic case right here. So what I say is that my string was a to the power k, b to the power k. Now what I say is that my string is now, I can represent this as something like a to the power p and then a to the power q and followed by a to the power k minus p plus q. So let me just write this as p minus q right here, or I could put a parenthesis here and say p plus q, and then b to the power k. The reason I've written it like this is because this is my x, this is my y and this is my z. So now what I have to do is I have to take x, y to the power I and then z, and I can take any I value that I want. So in our case, let's just take I to be 3. I'm just taking a random value here. Now what does my string become now? It becomes a to the power p followed by a to the power 3q now, because if there were q a's in y, now there's 3q a's because I wrote y 3 times, and then it will be followed by a to the power k minus p minus q b to the power k. This is my string now, and what we need to do is we need to see whether this belongs to our language, which is L, which is a to the power n b to the power n. And what I do for that is I count the number of a's here. I of course know that the number of b's is number of b equals k, and I need to count the number of a's. So number of a is equal to p plus 3q plus k minus p minus q, which is equal to k plus 2q. That's what I'm going to get. And assuming q is non-zero, which is a condition of the pumping lemma itself, that y here should be of length greater than or equal to 0. So my q cannot be 0. So if q is not 0, then the number of a's that I have is not equal to the number of b's. So number of a not equal to number of b, which means that this new string that I've got is not in the language a to the power n b to the power n. So that's the first case. The second case is something that you can also work out for yourself, but I'm just going to do it for the sake of completeness. So I have case 2 where y is in the b part, and in this case what happens is, once again I'll have to assume that my x can go on till the b part as well. So what I write is, I write a to the power k followed by a to the power k minus p minus q, followed by this is b to the power k minus p minus q, followed by b to the power p, followed by b to the power q. So what I'm saying here is that this is my x, this is my y, this is my z. One thing here is that we'll have to take care of the third condition as well, which says that the length of x and y put together should be less than p. So in our case it should be less than k, which is our pumping length. So that's something that we need to take care of, but even for the sake of this example, even if we don't take care of it, it's still fine. So what we do now is we take some I. So we want x y to the power I z, and then we take I is equal to, let's say in this case we take I is equal to 2. What happens now is I get something like a to the power k, b to the power k minus p minus q, because this is my x, this remains unchanged. Then I go with b to the power 2p, because I'm going to write b to the power p twice, so that's b to the power 2p followed by b to the power q. And now what happens is, what is my number of a? That's definitely k. What is my number of b? It's k minus p minus q plus 2p plus q, which is equal to k plus p. So this is my number of b right here, and assuming p to be again greater than 0, because it cannot be 0 if the length of y needs to be greater than 0, then the number of a's and the number of b's don't match, and as a result I can say that this again does not belong to my language. So number of a's not equal to number of b's. And I do have a third case as well, which is that y is in the a and b part. So case 3 is y is in a and b part. So this case is actually even simpler than the other ones. That's because what happens here is I can so my string is a to the power k, b to the power k. I write this as a to the power k minus p, followed by a to the power p, b to the power q, followed by b to the power k minus q. So this is my x, this is my y, and this is my z. Now what happens here is, when I take x, y to the power I and z, and I take I to be, let's say, any value, let's say I take 2, what happens is I say a to the power k minus p, which is my x, that remains unchanged. Then I write a to the power p, b to the power q, then a to the power p again, b to the power q again, and b to the power k minus q. So this actually breaks the pattern itself, so I don't even need to bother counting the number of a's and the number of b's, because I have these a's in the start, which is fine. Then once I start with the b's, I cannot have this a right here, so that's where it just breaks the pattern. So this is definitely not a to the power n, b to the power n. So these are all three cases that we have considered, in which we can divide S in X, Y, and Z. So we have done this step 4 right here, and we have shown that no division actually satisfies all three pumping lemma conditions. So we've already shown this as well. So having shown that, we've reached a contradiction here, because we have seen that no division that we have seen actually satisfies the pumping lemma conditions, which means that the pumping lemma is not holding for our language L that was given to us, which was this thing right here. The pumping lemma is not holding for this, and the only explanation of why the pumping lemma is not holding is that our assumption itself that L is regular was wrong. So this was wrong, and that is why I'm getting a contradiction at the end. Hence I can safely say that L is not regular, and that's how you would you would use the pumping lemma on any given language to prove that language is not regular. Once again, last time I'm reminding you, the pumping lemma can be used to prove that a language is not regular, but it cannot be counted as conclusive proof of a language being regular. So just keep this in mind. And that's it about using the pumping lemma. I hope you understood the pumping lemma from these 3 videos. If you did, don't forget to give the video a thumbs up, subscribe to my channel, and share the video with your friends. Guys, please remember to do this, and I'll see you next time.